Next, we have a bicycle manufacturer who builds racing, touring, and mountain biking models. The bikes are made of aluminum and steel. The company has a certain number of units of steel and a certain number of units of aluminum. And then we know the aluminum and steel requirements for each of them. The question is, how many of each type of bicycle should be made if we want to maximize profit given this amount of profit on each of the biking models? And we also want to know later what's the maximal amount of profit and whether this procedure requires all of the available units of steel and aluminum. If not, do they have any materials left over? So let's start by just setting up the problem. I'm just going to let x1 be the number of racing bikes they make, x2 will be the number of touring bikes they make, and x3 will be the number of mountain bikes that they make. So some people like to set up a little table with the information that we have. This is optional, so you can do this if you'd like. However, I normally just skip straight to setting up the initial simplex tableau. But do whatever helps you conceptualize the problem better. So you can write down a little table like this that records the coefficients on x1, x2, and x3, and also the corresponding total that we have for each of the different things that we're measuring here. We want to be maximizing the profit, but we also have constraints on the amount of aluminum that we have and the amount of steel that we have. So, and actually, I think I will keep them in this order. This is fine. Okay. So here, let's first focus on this top row where we have aluminum. So what we know is that the amount of aluminum that each of these bikes takes is 12 units, 21 units, and 15 units. And we have a total constraint of 42,000 units of aluminum. So we can't use more than 42,000 units of aluminum. We also know the amount of steel that each bike type takes, and the total amount of steel that we're allowed to use, which is 91,800. And then we know the profit for each bike type would be $8 for the first type, $12, and then $22 for the last type. And here, this is just equal to P, which is what we're trying to maximize. So we don't have any sort of cap here. We just want this to be as big as possible. And in previous problems, I've called this Z. I'm going to start just switching this up to whatever's natural in the given problem. So here, I'm just going to use P for profit, but it doesn't matter what letter you use. So we can use this table to set up the initial simplex tableau. So here we want to maximize the profit. And the profit is 8x1 plus 12x2 plus 22x3. I'm just reading off the coefficients from that bottom row there. So that's what we're trying to maximize, but it's subject to a few constraints. So we know we'll use 12 units of aluminum for each of the first type of bike times that many bikes, plus 21x2 plus 15x3, and that has to be less than or equal to 42,000. And we have a second constraint given by the steel, so that would be 17x1 plus 27x2 plus 34x3 has to be smaller than or equal to 91,800. And we also, of course, have the non-negativity constraints. These are just saying that you can't make negative amounts of bikes. So this is our linear program. And now we want to write the initial simplex tableau. So if you'd like, you can write down an additional equation that involves the slack variables. So because there are two inequalities here, or two constraints, we would have two slack variables that we need. We would also want to rearrange this initial equation so that all of the variables appear on this left side. However, once you start to get comfortable with this procedure, I normally skip that step. So if you understand that you just need to insert an S1 into this first inequality to turn it into an equation, and insert S2 as your second slack variable into the second inequality. And you also understand that by rearranging this top equation, you'll just be negating the coefficients over here on the right side. Then you can skip the intermediate step and just skip straight to writing down the simplex tableau. But if you need to take that extra step, then you're welcome to, and you can pause the video to work out what these should be if you need to. But this first equation should look like, or sorry, this first row should look like a 12, 21, 15, and then we added our first slack variable to the first constraint. So we would get a 1, 0, and then 42,000. Remember that on the right side of this vertical bar, I'm still just recording the coefficients that appear on the right side of these inequalities. The only difference is that now I'm identifying the bottom right entry over here in the objective row with the value of my variable p in this case. Okay, and then the second constraint equation would become a 17, 27, 34, 0, 1, 91,800. That's because we have to add our second slack variable to the second inequality. So what's going to happen in general with these slack variables is that you'll get sort of a diagonal ones matrix here. That's because for each new row, you're looking at a new equation, and each new equation has its own new slack variable. So you should have a diagonal ones matrix here. And then the objective row is going to have negated coefficients because we move everything over to the left side. So this would be in -8, -12, -22, and then zeros. Now, again, this is a little bit confusing, so I'm not a huge fan of this notation, but I do want to use the book's notation. So I am going to write P up here, but P is still, this column is still just recording the coefficients on the right-hand side. We're just identifying the bottom right number with the value of P at the current moment. So the coefficient here should not be a 1. That 1 would belong in the column for P, which we are suppressing. So we're deleting the column for P and instead just identifying P with this bottom right value. But technically, all three of these numbers in this column are just coming from the right sides of the equations. So this is what we have so far. This is our initial simplex tableau. And now the goal is to go through the simplex method to get rid of these negative indicators down here. We have 3 negative indicators to start with. So we target the most negative one first, and we need to compute the corresponding quotients in this column. So I take the far right number and divide by the numbers in the current column. Remember that I'm only doing this for the positive entries in this column. So I can ignore anything that's a 0 in this column, and I can ignore anything that's negative in this column. I'm only doing this for the positive entries. However, in this case, both of these entries are positive. So I'm going to do that for both. But if you compute the quotient, which you might want a calculator for, this would end up being a 2800 for the first quotient and a 2700 for the second quotient. Remember that that's this far right number divided by this number. So 42,000 divided by 15 is 2800, and then 91,800 divided by 34 is a 2700. You pick the smaller of those to give you the pivot row. So that means that because this is the smaller value, we'll be using that as our pivot row, and therefore 34 will be our pivot. So our next step is to turn that into a 1. To do that, I would just take the pivot row and divide by the pivot. And again, my main focus in this set of videos is mostly this new stuff up at the start of the problem, and then also in deciding how to choose our row operations. I'm not going to worry so much about doing the row operations by hand because we've already had a ton of experience with that. So don't stress too much about the individual row operations. I'm just going to record the matrix that we'll get after doing the row operation. So you can just trust me on these if you'd like. But we'll keep the first and last rows the same. So we'll still have this as our top row. And then the last row is still going to be -8, -12, -22, whoops, and then zeros all the way across. But our new middle row is going to have a 17 over 34, which if you'd like, you could reduce to a 1/2, and then a 27 over 34, which doesn't reduce, and then a 34 over 34, which is 1, a 0 over 34, a 1 over 34, and then we also have already computed this last entry. So we know that whenever you take 91,800 and divide it by 34, you should get 2,700. So this is the resulting simplex tableau. And we've got our pivot where we want it. It's now a 1. So next we will compute the next 2 row operations in a single step, because both of those involve just zeroing out the rest of the entries in this column. So I want to turn that 15 into a 0, and I want to turn that negative 22 into a 0 by using that pivot row. So that means I want row 1 minus 15 times the pivot row, and I want row 3 plus 22 times the pivot row. Oops. And if you'd like, you can pause the video now and just check that you're getting the same answer as me, especially if you want some practice working with these fractions. You might need some scratch work. I did this on scratch paper separately, but just to keep the videos short, I'm not going to work through all of the scratch paper. I don't think that would be especially enlightening. So instead, I'm just going to scroll down and I'll show you what we get after doing these row operations. But if you want some extra practice, you can pause the video now and figure out what you should get from these 2 row operations. But what I got is this. So I'm getting a 9/2, a 309 over 34, a 0, a 1, a negative 15 over 34, and then a 1500 as my top row. My middle row didn't change, so it's still 1/2, 27 over 34, 1, 0, 1 over 34. Let me redo that. And a 2700. And then my objective row will be updated to a 3, a 93 over 17 if you reduce, which you don't have to, a 0, 0, and 11 over 17, and a 59, 400. Okay, so this is what we get after doing those row operations. Again, you can, instead of working with fractions, you can use decimal values if you would prefer to do that. Just make sure that you round to a couple of decimal places so that we don't lose too much accuracy. Or if you want to be exact, then you can work with these fractions. I ordinarily would not be reducing these fractions. I just happened to in my notes earlier. But most of the time I would leave all of these fractions with the denominator 34, just so that whenever I do further row operations, these entries already have the same denominator, which makes them easier to add or subtract or whatever. Okay, so this is the simplex tableau that we get to, and this is actually the final simplex tableau because none of these remaining indicators are negative. So these are all positive indicators. I know that that first one looks like it might be a -3, but that's actually just supposed to be the closing bracket for the matrix. So that's a +3, and then a 93/17 and so on. So all of these are positive, or at least non-negative, and that means that we're done. So none of these are negative indicators. We can read off our optimal solution. To do that, I'm going to relabel the columns just to remind you what each one stands for. And now we can answer the questions that we wanted to at the beginning. So maybe I'll just write down what these actual values are. So I'll do this in a different color just so that I can mark out the matrix. So let's change to red maybe. So now I want to read off our solution from this simplex tableau. So I start by deleting any of the complicated columns. Remember, those are called non-basic. So x1 and x2 are non-basic because those columns have more than one non-zero entry. S2 is also non-basic. The last column we don't mark out. Remember, in the last column, I'm identifying this bottom right entry with P. So P will be 59,400. In other words, the maximal value for P is 59,400. That represents the maximum profit that we can obtain. So now we can use this information to answer the questions that we had. We know that the non-basic variables will be set equal to 0. So x1, x2, and s2 are all going to be 0 in the optimal situation. These others we'll need to read off equations for. So if I wanted to read off the x3 equation, it would be from this row, and it would say that x3 is equal to 2,700. And if I wanted to read off the value of S1, I would translate that top row into an equation. I would get that S1 is equal to 1,500. And lastly, we get that P is identified with that bottom right value again, so that would be 59,400. And now we can use this information to answer the questions that we wanted to. So in A, the question was how many of each type of bike should they make? And maybe let me scroll up to remind you what the different kinds of bikes were. So we can make racing, which was X1, touring, which was X2, and mountain, which was X3 models. So, and maybe we should also, while we're up here, remember what the slack variables corresponded to. So remember our first constraint equation here represented the amount of aluminum that we have. So the first constraint equation was for aluminum, and then the second constraint equation was for steel. So just keep that in your mind for now. That will become important whenever we answer this part C question, which is asking whether we have any units left over for steel or aluminum. Okay, so let me scroll back down to interpret this answer. So here we have X1 and X2 are both 0. So we would make 0 racing or touring bikes. And our entire production would be moved to mountain bikes. So we would make 2,700 mountain bikes. And one reason for this intuitively is that if you look back at the original setup for the problem, it may be that racing and touring bikes use less materials, but you make a significantly higher profit on the mountain bikes. So even though these are a little more efficient in terms of the material, we would be making more profit if we dedicated the more materials toward the mountain bikes. In other words, it's worth it to put the extra materials into the mountain bikes. But it's also possible in problems like these to get sort of a mixture of these, like you might want to make some number of mountain bikes and some number of touring bikes or whatever. But in this particular case, it's best for them to exclusively focus on mountain bikes. Question B was what's their max profit? For that, we just need to read off the value for the profit. So we know that the profit is 59,400. In part C, this is sort of a new question. We haven't talked about this so far, but this has to do with interpreting the slack variables. So the question was, do we have any extra materials left over? So remember that S1 was our first slack variable. That represents the amount of slack that we have in the aluminum constraint. And S2 was the amount of slack that we have in the corresponding steel constraint. So what we see here is that S2 is equal to 0. In other words, there is no slack in the steel constraint. So what that means is that we don't have any steel left over. We would be using all of our steel toward X1, X2, and X3. In this case, we know that X1 and X2 are both 0. So in other words, all of our steel would be consumed by the 2,700 mountain bikes. And you can go back and check your answer in a way here. If you just take the 2,700 mountain bikes and multiply that by the steel, the steel required for each mountain bike, you should get the total amount of steel that we want or that we have. So let me say that again because I sort of stumbled there. So if you take the total number of mountain bikes that we're making, which is 2,700, and then multiply that by the amount of steel that you need per mountain bike, that will end up equaling the total amount of steel that we had on hand. And that gives you a way of checking that the amount of slack in the steel constraint is actually 0. So if you wanted to check that, you could. I wouldn't do that normally unless, I was worried that something had gone wrong. But notice that we do have a non-zero slack variable. S1 is equal to 1,500. What that means is that if you look at the aluminum constraint, then the left side of the aluminum constraint inequality is smaller than the right side by 1,500 units. What that means is that our actual consumption is smaller than our limit by 1,500 units. Or in other words, the amount of slack that we have in the aluminum constraint is 1,500. We have that many leftover units. So we would have 0 leftover steel. and we would have 1,500 leftover aluminum. Okay, and putting that all together, we've answered all of the questions that we had for this problem. So now that we know how to interpret the slack variables, maybe let me scroll up to the previous problem for just a second and point something out. Notice that here both S1 and S2 were non-basic variables, so S1 and S2 would both be 0. That would also have an interpretation in this problem. So remember, in this problem, we had a constraint on floor space, and we also had a constraint on the budget. So we had a budgetary constraint and we had a square footage constraint for floor space. Having S1 and S2 both equal 0 just means that there's no slack in the budget and there's no slack in the square footage for floor space. In other words, we use all of the budget and we use all of the floor space available to us for this optimal solution. So the slack variables do have an interpretation, but it depends on what the inequality for that constraint actually represents. So in this second example, we knew that the first inequality represented aluminum here. So our first inequality represented aluminum, and therefore the first slack variable will be the amount of slack aluminum that you have. And then the second inequality represents steel, therefore the second slack variable will be the amount of steel slack that you have. So these do have interpretations, but we often don't really care about how much leftover material we have unless we're asked about it explicitly. Instead, we just want to know something like how many cabinets of each type should we buy, or how many of each type of mountain bike or whatever should we make. So unless I specifically ask for these slack amounts, I don't need you to report them. But it is important to know that those slack variables do have some sort of interpretation. It's just the amount of slack that you have in each of those constraints.